Now we will study about solar proton event. So what is a solar proton event? This is a type of space weather phenomenon characterized by a significant increase in the flux of high energy protons emitted by the sun, typically during solar flares or coronal mass ejections. So what is the radiation effect? The solar proton events emit high energy protons that can lead to increased ionization in the upper atmosphere that may influence ozone chemistry. And what are the stratospheric dynamics? The change in the atmospheric conditions caused by SPE, such as heating in the stratosphere, can affect circulation pattern. This alters the distribution and concentration of ozone in the Arctic region. So this is very important event that is happening in the Arctic region. How the ozone depletion takes place? The Arctic stratosphere can be influenced by SPEs, particularly during winter when conditions are favorable for ozone depletion. The increased reactive nitrogen species from the ionization can contribute to ozone loss. So basically the high energy protons are the one which basically ionize many other atoms. What is the long-term impact? While the individual SPEs have immediate effect, their cumulative impact over time can be contributed to broader trends in ozone depletion because various ions will be produced because of this event. And particularly when combined with other factors like greenhouse gas emissions and anthropogenic chemicals, this leads more destruction of ozone. See, the solar events are natural occurrences that produce hydroxy radicals, that is HOH and HO2, and nitrogen oxides NNO, NO2. All these constitute in the polar middle atmosphere, which are capable of influencing ozone. That means they all can react with ozone. The SPV produced hydroxy radical constituents are relatively short-lived and lead to short-term ozone decrease, that is hours to days. The longer-lived SPE produced NO radicals, nitrogen oxide radicals. They may influence the stratosphere over a period of months to years. Depending on the season in which the SPE occurred, they can impact ozone and other nitrogen oxide constituents like N, NO, NO2, NO3, N2O5, HNO3, HO2, NO2, and chlorine oxide with NO2, bromine oxide and NO2. So all these things can live for longer and they can destroy ozone. Here are the principal steps in the stratospheric ozone depletion. The first one is the emission of halogen source gases. That is what happens. And all these things are accumulated in the stratosphere. The emission of halogen source include CFCs and HCFCs. And then the short-lived gases are interfering here. That leads to tropospheric conversion, which produces reactive gases, and these reactive gases are converted into reactive halogen gases. The accumulated halogen sources from the troposphere is again transported to stratosphere. This absorbs UV absorption and then it again also gets converted into reactive hydrogen gases. But some of these hydrogen gases undergo conversion and they are moved back to troposphere. In the stratosphere, the conversion of reactive halogen gases really leads to various chemical reactions which basically destruct our ozone. And this ozone depletion variations happens through the spatial impact on ozone levels, and the destruction also leads to stratospheric air to troposphere return also happens, and finally in the end the ozone is basically destructed. So from the troposphere that moves through the stratosphere and then the ozone is basically destructed. So let us look at the impact of very short-lived substances on Arctic ozone. So what are these very short-lived substances? These are gases with atmospheric lifetime typically ranging from few days to weeks. These are produced primarily by oceanic sources such as phytoplankton and macroalgae. Some of the examples include methyl bromide, bromoform, dibromomethane and bromochlorocarbon. So basically all of them contain bromine. So how the ozone depletion takes place? The very short-lived substances contribute to the depletion of stratospheric ozone by releasing reactive bromine species. That's what we had seen. They all contain bromine. So they release Br and BRO, bromine oxide. And these are photochemically decomposed. The bromine is significantly more effective than chlorine at destroying ozone. This we had seen in the previous module. Then what is the transport mechanism? How these species are transported? The VLSs are emitted from the ocean surface and can be transported to the stratosphere through deep convection, particularly in tropical regions. Once in the stratosphere, they can have direct impact on ozone concentrations. So how do they affect the climate change? The climate change can be affected by the emission and the distribution of very short-lived substances. The changes in the ocean temperature, salinity and biological productivity may alter the production rates of these substances. This potentially leads to increased stratospheric bromine levels. And what are the regional effects? Basically, in the Arctic region, the impact on VSLS and ozone may be compounded by the climate change because the temperatures are increasing, which enhance the transport of these substances into stratosphere, because when the wind becomes hotter, the molecule starts moving up. This is particularly concerning during the Arctic spring when ozone depletion events are more pronounced. So the wind dynamics changes because of the higher temperature. And what is the modeling predictions? The climate models predict that the global temperature rise, the flux of VSLS to the atmosphere may increase, potentially leading to the further ozone depletion in the Arctic region. So what is the transport mechanism? One is by emission. The VLSs are emitted from the ocean surface into the atmosphere primarily through gas exchange influenced by concentration gradient and wind stress and turbulences. So these are all the mechanism by which they are emitted. And how the atmospheric transport takes place? Basically, once these VSLS are in the atmosphere, they are transported to stratosphere, particularly through the deep convection in tropical region and a vertical mixing process. So these are all the two things, because when the temperature increases, there is a hot air and cold air, so the vertical mixing happens very effectively. When we consider the photochemical decomposition, upon reaching the stratosphere, the VSLS undergo photolytic reactions. Basically, the bromoform decomposition is the main thing which produces bromine oxides. Bromoform reacts with photons to give CHBr2 and bromine dot radical, and CHBr2 again reacts with photons to give CHBr. This CHBr again is getting converted to C carbon radical, bromine radical and bromine oxide. So what is the transport mechanism for the ozone depletion? The reactive bromine species participate in the ozone destruction cycle. The reactions are given here. Br plus O3 gives BrO plus O2. BrO plus again oxygen radical gives Br plus O2. Each bromine atom now can destroy thousands of ozone molecules. So that is what is actually happening. So this leads to the complete destruction of ozone. The ocean emission of VSLS first happens, which is transported to atmosphere. Then there are two ways, either deep convection happens or the vertical mixing happens. This leads to photochemical decomposition in the stratosphere, because from the atmosphere they come to the stratosphere. Then they release the reactive bromine, which reacts with ozone to destruction of ozone. Then finally the ozone destruction cycle completes. So what are the different species involved? The total reactive nitrogen include NO, NO2, NO3, N2O5, etc. Oxygen is at the atomic oxygen, and hydrogen in the atomic hydrogen are the two things which are involved. OP3 means, the term symbol P3 means it is the atomic oxygen in the ground state with a triplet configuration, and H2 is molecular hydrogen. OD1 is again the term symbol for the singlet oxygen in the atomic oxygen. This is the first excited state for oxygen, because oxygen exists at the triplet in the ground state. OX are odd oxygens, oxygen or singlet oxygen or ozone or the oxidant like O3 plus NO2. HOX are basically odd hydrogen species, HOH, HO2 and H2O2. So here are the comparison between ozone depleting substances and very short-lived substances. So the definition is, what are ozone depleting substances? These chemicals that contribute to ozone layer depletion are called ozone depleting substances. And what are very short-lived substances? These are chemicals with a very short atmospheric lifetime. Some examples include the ODS are CFCs, halogens, carbon tetrafluoride, etc. And VSLSs are basically bromine or the halogen substances and some nitrogen compounds. Atmospheric lifetime include the ODS have a long lifetime, that is several years to decades, whereas VSLS are very short, days to months. and their ozone depletion potential, which is a very crucial factor. The ozone depleting substances have a very high ozone depletion potential. They can destroy thousands of ozone molecules per molecule of these substances, whereas VSLS have very low to moderate ozone destruction potential. What are the sources? The ozone depleting substances occur from the synthetic, from industrial and commercial applications. VSLS come from the natural sources basically. What is the impact? The ODS has a very significant impact. This leads to major stratospheric ozone depletion. VSLS have a very limited impact, often localized, and they are short-lived. What are the relevant equations? Cl plus O3 giving ClO and O2. And in the case of bromine reaction, which is an indirect contribution, Br plus O3 gives BrO plus O2. And how these are regulated? The ozone depleting substances are currently regulated by Montreal Protocol, but very short-lived substances we cannot regulate because it is a natural process. So we can only monitor this. What is the transport in the atmosphere? ODS can travel long distances in the atmosphere due to their stability. VSLS are rapidly degraded in the atmosphere. Here are the equations given. The atmospheric lifetime estimation is given as tau is the lifetime, k is the rate constant for decomposition, k is given here, k to the power minus 1. In the case of VSLS, the breakdown reaction is CH3Br in the presence of ultraviolet radiation gives CH3 plus Br. That is, methyl bromide decomposes under UV light, leads to its short lifetime. What is the reaction mechanism is actually given here, and the relevant reactions are like ODS, that is ozone depleting substance, participate in the ozone destruction directly through complex reactions. These are VSLS are often degraded quickly. What is the environmental impact? The ozone depleting substance have a long-term environmental effect. Very short-lived substances only have short-term effect.